Welcome to this episode of JEE Main Crash Program of Race 2022. Good evening, my dear students. Today, as you may be knowing, we are going to have a discussion of some questions belong to the chapters, basic principles of chemistry, atomic structure, and chemical bonding and molecular structure. As you know, in the JEE Main question paper, you have 20 multiple choice questions, which are mainly objective type, and 5 single digit answer questions, which also test your capability of answering numerical questions. Again, the theme being objective in nature. And we have about 2.5 hours for discussion. And I think we can have an overall survey of some of the important things relating to these 3 chapters. Usually, particularly for the last few years, it is seen that the JEE main paper contains problem type questions. Even in chemistry, you have problem type questions. And therefore, the chapter 1, basic principles of chemistry, in which you come across laws of chemical combination, Dalton's atomic theory, then the concept of atomic mass, molecular mass, empirical formula, molecular formula, how to calculate the empirical formula, molecular formula, etc. And the mole concept, balancing chemical equations, and problems based on mole concept, and also the concept of limiting reagent. All these things are covered in chapter 1, where you are likely to get numerical questions, problem type questions. And therefore, in this question paper, I have included about 11 questions from chapter 1, mainly numerical type. Even the objective type questions or the multiple choice questions contain problem type questions. And some 7 questions from atomic structure, and about 8 questions from chemical bonding. That's the composition of today's paper of discussion. I hope you are ready, and it is my pleasure to welcome all of you to this program, and a very cool good evening to each and every one of you. We will start the first question. What volume of 95% sulfuric acid of density 1.85 gram per milliliter and what mass of water must be taken to prepare 100 ml 15% solution of sulfuric acid of density 1.1 gram per milliliter? A numerical problem, not at all difficult. You have to take a particular volume of sulfuric acid, the concentration is given, the density is given, and you have to add sufficient amount of water to this volume of sulfuric acid to prepare 100 ml 15% solution of a density different from the previous density, that is 1.1. So how will we do this problem? Let us assume that the volume of sulfuric acid is VmL. It is VmL of sulfuric acid. And if it is VmL of sulfuric acid of 95% concentration and density 1.85, what will be the mass of sulfuric acid corresponding to this volume VmL? Volume into the density 1.85, that will be the mass, but it is only 95%, that means the actual mass is into 95 by 100. Okay? So that is equal to the mass of sulfuric acid in the second solution. In the second solution, volume is 100 ml, so the volume is 100 ml into the density is 1.1 into the percentage is only 15, so it is 15 by 100. So with regard to the VmL sulfuric acid that you have taken, the mass of sulfuric acid that VmL is V into 1.85 into 95 by 100. Okay? And the same mass of sulfuric acid is present in the second solution, 100 ml, 15% solution of density 1.1. So the mass is 100 into 1.1 into 15 by 100, which means these two are the same. These two masses are the same. That means you can equate the two. V into 1.85 into 95 by 100 is equal to 100 into 1.1 into 15 by 100. So you can solve this and get the value of V, and if you get the value of V, you will see that you can simplify it. It is not that complicated. You can simplify and get the value of V. You can do it right now if you want. You can get the value of V. V is equal to 9.4 ml. You will get the value of V from this relationship. The value of V is equal to 9.4 ml. That means the volume of sulfuric acid that you have to take is 9.4 ml. That 95% sulfuric acid, you have to take 9.4 ml. And what you have to prepare is 100 ml. That means you have to add water to this to make it 100 ml. And suppose we assume that there is no change in volume during the mixing, then this 9.4 ml plus what? Must be equal to 100. That means 100 is equal to 9.4 ml plus V dash ml. So that V dash is equal to 100 minus 9.4, that is equal to 90.6. Assuming that during diluting of the 9.4 ml sulfuric acid solution with water, there is no volume change during mixing, which may not be the case actually, and that's why in the answer given it is 92.6 gram water. Here it is 90.6 ml water, which is same as 90.6 gram water because the density of water is 1. So the mass is 90.6, and here the answer given is 92.6 gram. Of course, you can choose the correct answer by knowing the first answer. The first answer is 9.4 ml. So the answer of this question, the correct answer of this question is 9.4 ml sulfuric acid and 92.6 gram of water. 92.6 gram of water. Actually, when you solve it, you get a 90.6 ml, that is equal to 90.6 gram water, and the answer given is 92.6. Perhaps the slight difference is due to the fact that there may be some volume change during mixing of the two solutions, but it doesn't matter. Out of the 4 answers given, the correct answer is B, as you know, because the correct answer is judged by the first answer, that is 9.4 ml sulfuric acid. I hope it is perfectly clear. Okay, shall we move to the next question? Yeah, next question is again about stoichiometry. You can very carefully read the question. It is 20 gram iron pyrite. The formula is given, FeS2. it is roasted. Actually, the term roasted is a term in metallurgy where you heat the ore in presence of excess of air or oxygen to ensure complete oxidation of the metal ore into the oxide ore. So that is an information that you already have in connection with your metallurgy studies. So that wording roasting tells you that FeS2 is completely converted into its oxide, most probably ferric oxide, because with excess oxygen, when the ore is roasted, it is not ferrous oxide that is formed, but ferric oxide. So actually, the reaction would be FeS2 plus O2, the roasting giving ferric oxide, that is Fe2O3 plus sulfur dioxide. So that's the skeleton equation for the reaction. And what is done is, the sulfur dioxide gas so produced is absorbed completely in 400 ml NaOH solution. Okay? And if only 50% NaOH is used in the reaction, the molarity of NaOH solution is. That's the question. Actually, it's a good question. You must know the equation. It is FeS2 plus O2 giving Fe2O3 plus SO2. And you can balance the equation if you want. Even if you don't balance the equation, you can do the problem because it is FeS2 getting completely converted into Fe2O3. So whatever sulfur is there in FeS2 is completely oxidized to SO2. So even without balancing the equation, you can do the question very easily, because since there are two S here, the 2S will give you 2SO2. So S2 part of the compound will be oxidized into 2 sulfur dioxide. That means from 1 mole of the compound, FeS2, you will get 2 mole of sulfur dioxide. If you balance, of course, you will get it as 4FeS2. You can balance by the usual method, plus 11O2 giving 2Fe2O3 plus 8SO2. So that will be the balanced equation. But my humble suggestion is that you need not go on balancing the equation. You do not waste time for balancing the equation. You just understand that the sulfur content of the ore is completely oxidized into sulfur dioxide. So in 1 mole FeS2, you have 2 sulfur atoms, 2 moles of sulfur atoms, and the 2 moles of sulfur atoms are completely converted into 2 moles of sulfur dioxide. So from 1 mole FeS2, you get 2 mole. 1 mole FeS2, 1 mole FeS2 give 2 mole SO2. Okay? And what is 1 mole FeS2? You can get the molecular mass of this compound. Iron, you know that it is 55.85. For sulfur, it is 32. So that means 64. And that will give you 119.85. And that is roughly 120. You can take it as 120. So 1 mole FeS2 means 120 grams. Okay? That means 20 grams will be equal to 20 by 120 mole. So the amount of iron pyrites that you have taken is 20 by 120 mole. That is equal to 1 by 6 mole. Okay? So you have taken 1 by 6 mole of FeS2, and according to the equation, from 1 mole you get 2 moles of sulfur dioxide. So from 1 by 6 mole, you get 2 into 1 by 6. That is equal to 1 by 3 mole sulfur dioxide. So what you get in the reaction, the first reaction is, the roasting reaction is, you will get 1 by 3 mole of sulfur dioxide. I hope it is clear to you. The balanced equation is 4FeS2 plus 11O2 giving 2Fe2O3 plus 8O2. But you need not spend time on balancing the equation. You actually proceed like this. FeS2, roasting, complete oxidation to ferric oxide and sulfur dioxide. So the 2S in FeS2 completely converted into 2SO2. Okay? That means 1 mole of FeS2 gives 2 moles of SO2. 1 mole of FeS2 is 120 grams. By adding the atomic masses, you get the molecular masses 120. So 20 grams means 20 by 120, that is 1 by 6 mole and if it is 1 by 6 mole FeS2, that will give you 2 into 1 by 6, that is equal to 1 by 3 mole sulfur dioxide. Do you follow? Okay. And what is given in the problem is that this much sulfur dioxide now passed into, we will go to the previous problem. So, this much sulfur dioxide, that is 2 mole sulfur dioxide, 2 into 1 by 6, that is 1 by 3 mole sulfur dioxide, that is passed into 400 ml NaOH solution. And if only 50% NaOH is used in the reaction, the molarity of NaOH is something that has to be calculated. Okay. So, 400 ml NaOH solution, and what is the molarity of NaOH? But it is given in the problem that only 50% of NaOH have been utilized in the reaction. So, if you go to the next reaction, that is the oxidation of the sulfur dioxide neutralization reaction with the NaOH. This will be the reaction. Na2SO3 plus H2O. This is a usual acid-base reaction. SO2 is an acidic oxide. So, it is neutralized by NaOH. And what you find is 1 mole SO2 neutralized by 2 mole NaOH. It's a problem purely based on mole concept. So, 1 mole SO2 requires 2 mole of NaOH for neutralization, right? So, 1 by 3 mole SO2 formed in the first reaction will require 1 by 3 into 2, that is 2 by 3 mole NaOH for neutralization. Do you follow? So, but this used is 400 ml. So, what is, suppose the molarity is M for sodium hydroxide. What will be the number of moles of NaOH present in 400 ml? It will be given by 400 by 1000 into the molarity. That is actually the number of moles of NaOH present in 400 ml of the solution. But you find that only half is neutralized. Only half of this is neutralized. That means just half of this is neutralized by this much of sodium hydroxide. So, 400 by 1000 into molarity is equal to the number of moles of NaOH in 400 ml. So, that into half. Why? Because only 50% NaOH have been used. So, that must be equal to 2 by 3 according to this equation. So, you solve and get the value of M from this. You can get the value of M by solving this equation. So, that will be the molarity. Of course, I can solve here. So, it is 4M. So, this will be equal to 2 here. Okay. So, it is 2 by 10M is equal to 2 by 3. Therefore, M is equal to what will be the of the answers, various answers given? The answers will be 10 by 3, isn't it? I hope you understand the point. 2 by 3, the number of moles, that is equal to the number of moles of NaOH present in 400 ml of molarity M into half, because only 50% of NaOH was used in the reaction, right? So, it is 400 by 1000 into molarity, that is the number of moles in 400 ml. So, that into half, that must be equal to 2 by 3. Solve and get the value of M, and you will see that the correct answer is B. B is the correct answer. B, 10 by 3 is the correct answer. You can solve and get the value of M. You will get it as 10 by 3. So, that is a problem. Remember that it is a good problem. In my humble opinion, it's a good problem because it tests so many things. Whether you are familiar with the oxidation of ferrous sulfide or iron pyrites, it is not ferrous sulfide, it is iron polysulfide. Normal ferrous sulfide is FeS, but iron pyrites is FeS2. FeS plus S, that is FeS2. And on roasting, it is completely converted into ferric oxide, and sulfur part of the ore is converted into sulfur dioxide. This is something that you study in metallurgy. So, that information is a prerequisite for doing this problem, and then you must know about the mole relationship, the equation and the mole relationship, for the first reaction as well as for the neutralization process. You must know the mole relationship, and then you will be able to work out the problem. Only thing is that it takes some time for working out this problem. As you know, for 25 questions you get 1 hour. That means on an average you have 2.4 minutes for answering a question. But there may be some questions which are pretty easy, which may take hardly 1 minute or so. So for problems of this type, questions of this type, you will get more time for working out, and you can work out this question because it is not at all complicated, not at all difficult. Only thing is that you must know the mole relationship in the case of the two reactions. One is oxidation of FeS2 into Fe2O3 and sulfur dioxide. There it is a FeS2, and therefore it will give 2 SO2. So the mole relation is immediately known. 1 mole gives 2 mole SO2. When you calculate corresponding to 20 grams, it is 20 by 120, that is 1 by 6. 1 by 6 mole of FeS2 gives 2 into 1 by 6, that is 2 by 6. Okay, so much mole of sulfur dioxide, and from this you come to the next equation, SO2 plus 2 NaOH giving Na2SO3. So for 1 mole you have 2 mole NaOH, therefore 1 by 3 mole you have 1 by 3 into 2, that is 2 by 3 mole, and that 2 by 3 is equated to the amount of the mole of NaOH in this 400 ml NaOH solution into 50%. So 400 by 1000 into molarity will give you the number of moles in 400 ml. So that into half will be equal to the sodium hydroxide actually utilized, which is equal to 2 by 3. So you can equate the two and solve, and thereby get the value of the molarity, which is 10 by 3. In my humble opinion, it's a good question. It's a good question. And now come to question number 3. I told you that out of the 25 questions, all questions will not be difficult. There will be actually some 8 questions on an average, which are comparatively simple questions, which an average student can very easily answer. And there may be some another 10 questions which may be of higher standard, and there may be some 6 or 7 questions which are really of a high standard. That will be a usual composition of a JEE main question paper. You must have seen so many previous question papers, and if you carefully analyze that, you will get this sort of an impression that there will be some questions which are pretty easy, and here is a question which is pretty simple, and one can do it in within seconds. This problem, how many moles are present in 12 into 10 raised to 23 molecules of ethyl alcohol? So how will you do the problem? You know that 1 mole, it is the Avogadro number of molecules. 1 mole is equal to 6.02 into 10 raised to 23 molecules. That's the basic idea which every one of you may be knowing. 1 mole contains 6.02 into 10 raised to 23 molecules. So the question is, how many moles are present in 12 into 10 raised to 23? So the number of moles will be given by 12 into 10 raised to 23 divided by 6.02 into 10 raised to 23. That not 2 can be omitted. For simplicity, it is 12 by 6. So approximately 2 into 10 raised to 23 by 10 raised to 23. So what you get is 2. So the question is readily answered within few seconds. It is 2 mole. As I told you, there will be some questions which are pretty simple. In any question paper, maybe at least a few questions which are pretty simple. And just to have a representative nature for the question paper, we have included some simple questions too in this question paper. Okay, so this is one such question. The question is very easily answered by all of you, I suppose, and you will get the answer 2 mole. Okay, so coming to the 4th question. Now read the question very carefully, because this question again is not that simple, because one must know many things as a prerequisite for solving this problem. It's of course a problem again based on mole concept, then principle of titermetry and all that. But the first part of the question, you read it very carefully, X small KiO3, potassium iodate, KiO3, is treated with excess of Ki. So it's a reaction between potassium iodate and potassium iodide, or more correctly, between the ions IO3 minus and I minus. So this is something that you study in connection with group 17, chemistry of the group 17 elements, that is the halogens, in the second year. So this is a question which is not just purely based on chapter 1, but the principles in that chapter linked to certain things that you study in the group 17 chemistry, the chemistry of the halogens. So this is the reaction IO3 minus plus I minus. So what is the product? When IO3 minus and I minus react. And similarly, there is a reaction between BrO3 minus and Br minus, the bromide-bromate reaction. And this is the iodide-iodate reaction. And for this reaction, iodide and iodate, at least some of you may be knowing, it is a reaction. The reaction is this one in presence of H plus, of course, that is understood, to give 3I2, 5I minus plus IO3 minus, okay, that's the reaction, giving 3I2 plus 3H2, and obviously you will require 6 H plus ions. So this equation you must know. This is a prerequisite for doing this problem. If you are not aware of this equation, if you don't remember this equation, you cannot proceed. So this is the basic thing. So you have taken X mole of KiO3. This is X mole. It is given X mole. Okay. And then that X mole IO3 minus will require actually 5 mole I minus, but that is not important here. What is given is excess Ki. That means the reaction is complete. With whatever I minus required, the reaction is complete because you have taken excess of potassium iodide. So that X mole of IO3 minus would have completely reacted and converted into 3 moles of I2. 3 moles of I2. According to the balanced equation, you find that X mole of IO3 minus. Here the balanced equation is very important. IO3 minus plus 5I minus plus 6H plus giving 3I2 plus 3H2. This is again an equation perhaps you might have balanced in connection with the redox reactions. And if you are very thorough with that, then you can immediately write down the equation. So that is important here. Otherwise, you are likely to make mistakes. So you must know this equation. IO3 minus plus 5I minus plus 6H plus giving 3I2 plus 3H2O. X mole IO3 minus give 3 moles I2 for 1 mole, and for X mole you will get 3X mole. For 1 mole you get 3 moles, and therefore for X mole you will get 3X mole. The liberated iodine, which is dissolved in freshly prepared starch solution. You know that iodine reacts with the sodium thiosulfate quantitatively, and that actually forms the basis of titrations called iodometric titrations and iodimetric titrations. Iodimetric titrations are those where iodine is directly titrated against sodium thiosulfate, and iodometric titrations are those in which generated iodine by a reaction is titrated against sodium thiosulfate. So here is in this case it's a generated iodine. Iodine is generated by this reaction, which in turn is titrated against sodium thiosulfate. And you know the starch is used as an indicator, and the starch gives a blue color with iodine. So long as iodine is there, you have a blue color in the solution, and on titrating against sodium thiosulfate, the iodine reacts with sodium thiosulfate, and that equation is also important. The reaction of sodium thiosulfate with iodine giving sodium tetrathionate and sodium iodide. You might have studied that reaction also, but that equation is not very important here as far as solving the problem is concerned. And here actually that reaction would be Na2S2O3 plus I2 giving Na2S4O6 sodium tetrathionate plus NaI. That is the equation. 2Na2S2O3 plus I2 giving Na2S4O6 plus 2NaI. That's the reaction. Okay. For the titration of iodine against sodium thiosulfate, I2 plus 2Na2S2O3 gives Na2S4O6. The compound is sodium tetrathionate. That also is an important reaction, you must know, plus 2NaI. And here the stoichiometry is for 2 moles of sodium thiosulfate, 2 moles, you have 1 mole of iodine react. And actually, in the actual titration, when you titrate against sodium thiosulfate, I told you the blue color of the starch iodine complex will get gradually, the blue color will be diluted, and once the iodine is completely reacted away, the solution will become colorless, and you will see the formation of the starch once again in the solution, and the whole solution will become turbid. So that's why until white precipitate was obtained. So what is important is the blue color. The blue color is, once the blue color disappears, one can conclude that the reaction is complete. And in the solution, there will be white turbidity of that starch and whatever sodium tetrathionate and sodium iodide formed. Of course, these are soluble substances, and the white precipitate is actually due to the starch which was originally added to form that blue starch iodine complex, the color of which is something which can be monitored so as to find out the end point of the titration. I hope the chemistry is this. So the first part of the chemistry is IO3 minus plus 5I minus plus 6H plus giving 3I2 plus 3H2O. That's the first part of the chemistry. And there the stoichiometric relation you find is X mole IO3 minus giving 3X mole I2, 3X mole, 1 mole, 3 mole. Therefore, for X mole, you get 3X mole. Okay. And for the second reaction, 2Na2S2O3 plus I2 giving Na2S4O6 plus 2NaI. And for that equation, you find 2 moles of Na2S2O3, 2 moles of Na2S2O3 react with 1 mole of I2. And therefore, if it is 3x mole of I2 that have formed in the previous reaction, the 3x mole of I2 will require 3x into 2, that is equal to 6x mole Na2S2O3. So the amount of sodium thiosulfate used, is 6x moles, 6x moles. Okay? So remember that it is 6x moles. 6x moles of sodium thiosulfate. 6x moles of sodium thiosulfate. Now, this much sodium thiosulfate is the thiosulfate that is present in 60 ml 0.1 normal sodium thiosulfate. Remember that sodium thiosulfate, the normality will be the same as molarity, because the equivalent mass of sodium thiosulfate is same as molecular mass, which follows from the previous equation, 2Na2S2O3 plus I2. So 2Na2S2O3 require 2 equivalents of iodine. So 1Na2S2O3 require 1 equivalent of iodine, 1 equivalent of I. Therefore, the equivalent mass of sodium thiosulfate is same as molecular mass. And that is something that you already studied by heart, I think. The equivalent masses and molecular masses of common substances of importance as far as titration is concerned will be already familiar to you, and most of the students study them, those values by heart too. So remember that for sodium thiosulfate, you need not know the exact value, but you must remember that the equivalent weight is same as the molecular weight. So the 0.1 normal sodium thiosulfate is the same as 0.1 molar sodium thiosulfate. Normality and molarity will be the same, provided equivalent weight and molecular weight are the same, which is true for sodium thiosulfate. So that 0.1 normal sodium thiosulfate is exactly the same as 0.1 molar sodium thiosulfate. And if it is 60 ml, 0.1 molar sodium thiosulfate, what is the number of moles present? The number of moles present will be 60 divided by 1000 into 0.1. 60 divided by 1000 into 0.1. So that must be equal to that 60 divided by 1000 into 0.1. That is equal to 0.006 mole. Okay, and the 0.006 mole must be equal to 6x. You already calculated it to be 6x in the previous equation. So you can equate 6x is equal to 0.006, from which you can find x. X is equal to 0.001, that is 10 raised to minus 3. It's a good question. The question requires so many things as prerequisite. You must know so many things. One is the bromate-bromine reaction or the iodate-iodine reaction. In this case, it is iodate-iodine reaction. The same is true of bromate-bromide. BrO3 minus and Br minus will give Br2. A similar equation. Okay, remember that also. In this case, it is iodate-iodide reaction, and the product is I2. You must know the balanced equation, and from which you must be able to find out the mole equivalent of iodine that is there. And then the next equation you must know, it is a reaction between iodine and sodium thiosulfate to give sodium tetrathionate and sodium iodide. For that also you must know the balanced equation and the mole relationship. And once you know the mole relationship corresponding to the iodine that is formed in the first equation, what is the amount of sodium thiosulfate reacted in the second equation? You have to find out. And thereby calculate the number of moles of KiO3, potassium iodide. We had assumed it to be x, and the value of x is 0.01, that is 10 raised to minus 3 mole. Okay, so it's a good question in my opinion. Good question, testing so many things, and unless you are thorough with all these things, you won't be able to answer such questions. So that's of course, in my humble opinion, it's an above average question, a good question about titration, the titration between iodine and sodium thiosulfate using starch as the indicator. That is actually the experimental basis of the question, and the previous knowledge that you must have is the iodate-iodide reaction. Remember, you can refer that group 17 elements, the chemistry of the group 17 elements, you will find this equation there. It is iodate, and you can also refer the equation in balancing of redox reactions. Most probably this equation will be there in the text or in any guide for that matter. This equation is usually the one that is worked out in the class, the iodate-iodide reaction. So if you are familiar with that, and if you know the correct equations, then there is no complication regarding the problem. You can easily work out the problem, but it's a good question in the sense it tests so many of your possessed knowledge about so many things, balancing of equations, equivalent weight relationship for sodium thiosulfate. Equivalent is same as molecular weight, and the normality is same as molarity. Remember that for sodium thiosulfate. I think it is clear. We will next move on to the next question. Okay. Okay. Yet another question based on weight volume relationship. Now this molecule is very familiar to you. It is the sulfur molecule, S8 molecule, the rhombic sulfur. Has an S8, the atomicity of rhombic sulfur is 8. It exists as S8 molecules, and this is the geometry. This is the way in which the 8 sulfur atoms are connected. That also you know. Actually the diagram need not be given in the problem, but it is given. Even if it is not given, you must know it. Anyway, it is S8. It's already given in the problem. In rhombic sulfur, the sulfur atoms are joined into S8 molecule. That is given in the problem. And you are given the density of rhombic sulfur. The density of rhombic sulfur is given. And the question is number of S8 molecules in a crystal of 0.568 millimeter cube. So you are given the volume of the crystal, you are given the density of the crystal, and once the volume of the crystal is given and the density is given, you can very easily calculate the mass of the crystal, isn't it? Density is mass by volume, so mass is equal to volume into density. So mass is equal to volume into density, and here the volume is given in millimeter cube. You have to be careful about the units. It is mm cube, volume in millimeter cube, and the density is given in gram per cm cube. So you convert the millimeter cube into centimeter cube. You know that 10 millimeter is equal to 1 centimeter. So millimeter cube into 10 raised to minus 3 will be equal to the volume in centimeter cube. So the volume is 0.568 into 10 raised to minus 3, so many cm cube, multiplied by 2.07 gram per cm cube. Now the units are okay. The volume in cm cube and the density is gram in cm cube, gram per cm cube. Okay. So you can calculate and get what the mass is. You can do it right now. You can calculate and get the mass. And once you get the mass, then it is damn easy to calculate the number of moles. This number of moles is equal to mass by molecular mass. And here it is S8. S8 means the atomic mass of sulfur is 32. So 32 into 8, it is 256. So the number of moles will be equal to, number of moles is equal to the 0.568 into 10 raised to minus 3 into 2.07, so many gram, divided by the gram molecular mass, that is 256. So that will be equal to the number of moles. Of course, in working out these problems, actually you can have some approximation to get the result quickly. If you do it in the routine way, perhaps it may take more time for calculations of this type. Sometimes they give values which could be easily multiplied or easily divided, but here it is not that easy. You can multiply by 2 instead of 2.07, or you can take it as 2.1, approximately 2.1. You multiply 0.568 divide by 256, you will get the number of moles. And to convert into number of molecules, the number of moles have to be multiplied by the Avogadro number. So number of molecules will be equal to number of molecules is equal to this much, the number of moles, okay, you can post the value here, multiplied by 6.02 into 10 raised to 23. So that 0.568 into 2.07 by 256 into 6.2 you have to calculate and look into the answers. Which of these is the correct answers you have to decide, and you will see that for question number 5, the number of the answer that you get is this one, the last answer, that is D is the answer that you get, 2.765 into 10 raised to 18. You do the calculation yourself, 0.568 into 10 raised to minus 3 into 2.07 by 256 multiplied by 6.02 into 10 raised to 23. I hope you can hear me. Something is followed. You can do the calculation yourself. I am not doing the word by word calculation here. I have written the steps, I have written the values, and you can calculate yourself and decide which is the correct answer. And it is 2.765 into 10 raised to 18. I think that will be the correct answer. D is the correct answer for this question. Okay. I think the method is clear. It's a very simple problem. You are given the volume, but in millimeter cube, you have to convert into centimeter cube by multiplying by 10 raised to minus 3. Okay. And then multiply by the density so as to get the mass, right? And once you get the mass, you can calculate the number of moles by dividing the mass by molecular mass. Okay, molecular mass is calculated knowing that it is S8, 32 into 8. Okay, 32 is the atomic mass of sulfur, everybody knows. For simple elements, the atomic masses are already known to us, so perhaps they may not give the atomic masses in the question. For certain other elements, perhaps for iron they may give it as 55.85, for chlorine they may give it as 35.5, but for simple elements the atomic mass may not be given in the problem, so you must know that for sulfur the atomic mass is 32, so 32 into 8 will be the molecular mass of S8. So the mass divided by molecular mass, you will get the number of moles, and once you get the number of moles, it is so easy to convert into number of molecules by multiplying by the Avogadro number, that is 6.02 into 10 raised to 23. You can multiply by 6 into 10 raised to 23, that will be okay, and you will get the result. It is 2.765 into 10 raised to 18. So it is not at all a difficult problem. It is a simple problem, not that simple, because you must know the steps. That's very important. You have to take care to do the numerical calculation to get the appropriate answer. That's very important. Okay, now is question number 6. Read the question carefully. Is pure nitrogen dioxide is formed when dinitrogen oxide, N2O, is also called a nitrous oxide, and oxygen are mixed in the presence of a certain catalyst. Okay, what volumes of N2O and O2 are needed to produce 4 liters of nitrogen dioxide if all gases are held at the same conditions of temperature and pressure? Now the very last clause in the question tells you that it is a question about the Gay-Lussac law of gaseous volumes. There is a simple relationship between the volumes of the gaseous reactants and gaseous products. In a reaction which is gaseous, where the reactants and products are in the gaseous state, there exists a simple ratio between the volumes of the reactants and also the gaseous products, provided all the volumes are measured under the same conditions of temperature and pressure. And that's a statement of the Gay-Lussac law of gaseous volumes. And if you balance the equation, where you have shown the gaseous reactants and the gaseous products, of course the stoichiometric coefficients will give you the numerical values in the volume ratio relationship. So it is pretty simple. The problem is very simple. It is N2O reacting with O2 giving NO2. That's the reaction. So you can balance the equation. It is 2N2O giving 4NO2, and you require 4 into 2, 8 oxygen, 2 and 2 are already here, so you will require 3 O2. Okay? So this is the balanced equation for the conversion of nitrous oxide into nitrogen dioxide in combination with oxygen. It is 2N2O plus 3NO2, 3O2 giving 4NO2. Okay? In this context, it may be good if you remember all the nitrogen oxides. Nitrogen is an element which gives so many oxides, as you know. You have the nitrous oxide, you have nitric oxide NO, you have dinitrogen trioxide N2O3, you have nitrogen dioxide NO2 and its dimer N2O4, and then you have nitrogen pentoxide N2O5. So these are the oxides of nitrogen, and this particular question about nitrous oxide combining with oxygen forming nitrogen dioxide in the presence of a catalyst. So this is the balanced equation written, and all these are gases. That means you can readily apply the Gay-Lussac law of gaseous volumes. the ratio of the volumes of the combining gases and the gaseous product will be given by the ratio of the stoichiometric coefficients of the balance equation. So naturally the ratio will be 2:3 for volume of N2O and volume of O2. 2 volumes of N2O will combine with 3 volumes of O2 to give 4 volumes of NO2. So the ratio between the volumes of N2O and O2 to give 4 liters of NO2 will be 2:3. 2 liters of N2O and 3 liters of O2 combined to give 4 liters of NO2, because according to the equation, 2 volumes of N2O plus 3 volumes of O2 giving 4 volumes of NO2. Do you follow? So the ratio is 2:3, and obviously the answer is B. It's a very simple question, can be answered within seconds, provided you can write the balanced equation for the problem. It is pretty simple. Balancing these equations simple. But the question is your familiarity with this Gay-Lussac's law of gaseous volumes. Okay? I hope it is clear. There is no confusion about it. It's a very simple question, very straightforward question, not at all complicated. You need not do so many things there. It is just the volume ratio, it is 2:3. To get 4 volumes of NO2, and if it is 4 liters, you require 2 liters of N2O and 3 liters of O2. The ratio of the volumes is 2:3. Okay? Okay? Yes. Yeah. So this again is a question on stoichiometric calculation. You must know the mole relationship, and the reaction is between 100 ml barium chloride solution, and you are given the weight of BaCl2 in volume, that is per 100 ml, that is given, it is 20.8%. You are given the mass bar volume percentage, it is 20.8%. That means 20.8 gram is present in 100 ml. And you have taken 100 ml. So it will contain obviously 20.8 gram BaCl2, and it was mixed with 50 ml potassium sulfate solution. Again, the mass percentage of potassium sulfate is given, it is 17.4. That means 17.4 gram potassium sulfate in 100 ml. Okay? So the reaction is between BaCl2, this BaCl2 plus potassium sulfate. It's a very simple precipitation reaction. You have BaSO4 plus 2KCl. That's the reaction. Anybody can balance the equation. Very simple. So 1 mole BaCl2, again the mole relationship, 1 mole BaCl2 will react with 1 mole K2SO4 to give 1 mole BaSO4. Actually, in problems of this type, they ought to have given the atomic mass of barium, because it is not, all the students may not be remembering the atomic mass of barium. I tell you, the atomic mass of barium is 137. It will be neglect in the decimal places. I have written just 137 for barium. And for chlorine, you know, 35.5, so 71. So that will make you 208. So 1 mole means 208 gram for barium chloride. Similarly, for potassium sulfate, taking the atomic mass of potassium as 39, it is actually 39.1. You can neglect that 0.1. Take the atomic mass of potassium as 39, so it is 2 into 39, that is 78. Okay, for sulfur it is 32, for 6-oxygen it is 64. It is 174. So 1 mole K2SO4 means 174 gram, right? To give barium sulfate, you can also calculate the molecular mass of barium sulfate. It is 137 plus 32 plus 64 will make you a total of 233. Again, excluding the decimals, which are very small values, we can ignore when compared with the large value 233. So you have 1 mole barium sulfate, that is 233 gram. So you have the mole relationship and you have the mass relationship. 1 mole of BaCl2 is 208, 1 mole of K2SO4 is 174, and 1 mole of BaSO4 is 233. But what is given in the problem? It is 100 ml BaCl2 solution. Mass percentage is 20.8. So that 100 ml BaCl2 solution will contain actually 20.8 gram barium sulfate, barium chloride, and it was mixed with 50 ml K2SO4 solution. If it is 100 ml, it will contain 17.4. Okay? The mass percentage, mass bar volume percentage is 17.4. So if it is 50 ml, just the half of that, it will be 17.4 by 2. 17.4 divided by 2 gram potassium sulfate. 8.7, isn't it? It is 8.7 gram. 8.7 gram potassium sulfate. So theoretically, 208 gram barium chloride will react with 174 gram potassium sulfate, or 20.8 will react with 17.4. But here you have taken only 8.7 gram of potassium sulfate, which means potassium sulfate is the limiting reagent. Limiting reagent means the reagent which decides the extent of the reaction, the reagent which decides how much product would be formed, because this is a reagent in lesser amounts than required from the mole ratio. Okay? For the mole ratio, it must be 17.4 for 20.8 gram barium chloride, but you have taken only 8.7 gram, which means 20.8 barium chloride, even though present, only half of that will actually take part in the reaction. Only 10.4 will take part in the reaction. So when 8.7 gram K2SO4 reacts, how much of barium sulfate will be formed? If it is 17.4, you will get 23.3. 23.3. If it is 174, you will get 233. If it is 17.4, you will get 23.3. 23.3, okay? And if it is 8.7, you will get 23.3 divided by 2 mole of, divided by 2 gram of barium sulfate. I repeat, for 1 mole barium chloride, you have 1 mole potassium sulfate and 1 mole barium sulfate if there is complete reaction. And here 1 mole is 208 for barium chloride, 1 mole is 174 for potassium sulfate, and 1 mole is 233 for barium sulfate. But you have taken only 100 ml containing 20.8%, which means 20.8 gram in 100 ml, mixed with 17.4 in 50 ml. 17.4 percentage, but you have taken only 50 ml. That means 17.4 by 2, that is 8.7 gram potassium sulfate. So corresponding to this 8.7 gram potassium sulfate, that is half of the quantity 17.4. The barium sulfate that will be formed in the reaction will be half of this quantity, that is 23.3 divided by 2. Now what is the problem? The white precipitate formed is, what is the white precipitate form? The white precipitate formed is 23.3 by 2, 23.3 by 2, and what is the value? The value is 11.6 something, so many gram, 11.65 gram, that's the answer. So the answer is B, the correct answer is B, but it's a problem, it's a normal problem where that concept of limiting reagent is involved, but question is not, nothing is asked regarding the limiting reagent, but we understand that potassium sulfate in this reaction is the limiting reagent. It limits the amount of the product in the reaction, because actually the product would be, ought to be 23.3 for 28.8 gram barium chloride, provided you supply 17.4 gram potassium sulfate. But here he has supplied only 8.7 gram potassium sulfate, which means the amount of barium sulfate formed will be just half of the quantity, 23.3, that is 11.65 gram. It's a pretty simple problem which includes the concept of limiting reagent, and 3 molecular mass calculations there. The atomic weights are not given in the problem, but I tell you, for problems of this type, at least for barium, they will give you the atomic mass as 137. For chlorine, sulfur, etc., the values will not be given because these values are already very, very familiar to you students. But for barium, some students may not be knowing. So in such problems, they ought to give the atomic mass of barium. In the bracket, it is given 137. In this problem, it's not actually given, but I tell you, it will be usually given for elements like barium. If you go through the JEE question papers, you will see that for such elements, the atomic masses are given in bracket. Okay, so that's a problem. Again, a problem on mole concept involving the concept of limiting reagent. The equation is pretty simple. Barium chloride plus potassium sulfate giving barium sulfate. The white precipitate formed is barium sulfate, and this reaction, recall, it is usually used as a test for sulfate ions in qualitative analysis. To the solution of the sulfate, you are adding barium chloride solution. You observe the formation of the white precipitate, that is barium sulfate. So from that point of view also, the reaction is important. Okay. So that's all I would like to mention about this particular problem. Yeah, this is a very standard question, a question which has been asked many times, a very standard question. The molarity of solution obtained by mixing 750 ml of 0.05 molar HCl with 250 ml of, again, HCl of a different molarity. So HCl solution of one particular molarity is mixed with HCl solution of another molarity, and the question is, what will be the resultant molarity of the solution? I think all of you might have studied this relationship. M resultant molarity M is equal to, what's the relationship that you have studied? It is M1 V1 plus M2 V2 divided by V1 plus V2. M1 is the molarity of the first solution, and V1 is the volume of the first solution. M2 is the molarity of the second solution, and V2 is the volume of the second solution. Then the resultant molarity is given by M1 V1 plus M2 V2 divided by V1 plus V2. Okay, and here both are HCl, both are monobasic acids, so there is no confusion about molarity, normality, etc. For HCl, molarity and normality are the same. So both are HCl, so you need not worry about the equivalence and all that. Here you can straightaway apply the relation M1 V1 plus M2 V2 divided by V1 plus V2. You can substitute and get the result. It is 750 plus 750 into 0.05 plus 250, okay. So that into 2 divided by V1 plus V2, that is equal to 1000. You can get the result. If it is not seen, I write once again here 750 into 0.05, okay, plus 250 into 2 divided by 750 plus 250. So that will be the resultant molarity. You can calculate and get the result, and you will get the result. What will be the resultant molarity? It will be 0.875. This is 0.875 molar. What is to be studied during the discussion is how to work out the problem. It is not the numerical answer which we are interested actually now. What is important is how to solve the problem. How to solve the problem. What is the basic principle underlying the problem, and what is the method of solution? That is what you have to find out. So this is the relationship that you have to bear in your mind. to calculate the resultant molarity. I hope you follow the point. It is HCl of one particular molarity mixed with HCl of another particular molarity. And the resultant solution, what will be the molarity is a question. So straight away you can apply the relation M is equal to M1 V1 plus M2 V2 by V1 plus V2. You can get the molarity of the resultant solution. So that's again, as I told you, some 10 questions out of 25 questions, nearly 8 to 10 questions will be simple questions, and this is obviously a simple question of the first type. The easiest question. There is a bunch of easiest questions, very easy questions, about 8 to 10 questions. So this particular question belongs to that category. Not too much thinking is required. Only thing is that you recall this relation from your mind to substitute and solve the problem. Okay. And we will, a very small break of some 1 or 2 minutes. Okay. Welcome back. So let us now move to question number 9. 0.31 gram of a nitrogen containing compound on reaction with NaOH gave ammonia. which required 100 ml of 0.1 normal HCl. Then you are asked to calculate the percentage of nitrogen in the nitrogen containing compound. Perhaps when you read this question, you may be recalling the Gelder's method for the determination of nitrogen in organic compounds. But the whole thing about Gelder's method is not given here in the problem. This can well be applied to an inorganic compound containing nitrogen, for example, ammonium chloride. Ammonium chloride on reaction with the sodium hydroxide gives ammonia, you know, and ammonium salt on reaction with NaOH gives ammonia. So whether it is an organic compound or inorganic compound, it's immaterial. So here focus on the data that is given. Of course, one can have that the Gelder's method in your mind, that's okay. But the problem you can approach again from the basic point of view, from the basic chemistry involved in the reaction. It's a nitrogen containing compound, on reaction with alkali. On reaction with alkali, the nitrogen containing compound gives off the nitrogen in the form of ammonia. Okay, you get ammonia. And you have taken 0.31 gram of the nitrogen containing compound. This is nitrogen containing compound. The nitrogen containing compound may be an ammonium compound, an ammonium chloride or anything of that sort, which on alkali treatment gives ammonia. Now we are interested in that ammonia and we are interested in the amount of HCl that is required for neutralizing the ammonia. The question is based on that. So the formula of the compound is not important here. So that's why I am not at all writing the formula of the compound. It may be any compound for that matter, which can give ammonia on reaction with alkali. Okay. It is 0.31 gram of the compound on reaction with alkali gives ammonia, and this ammonia required 100 ml 0.1 normal HCl, 0.1 normal HCl for neutralization. That's the point. 100 ml 0.1 normal HCl for neutralization. And the neutralization reaction between ammonia and HCl is again pretty simple. NH3 plus HCl giving NH4Cl. That is a simple reaction. So for NH3, you require 1 HCl. For 1 NH3, you require 1 HCl. Okay? Or for conversely, for 1 HCl, 1 NH3 has to react. So 100 ml 0.1 normal HCl would have completely reacted with 100 ml 0.1 normal ammonia. I hope you understand the point. The point of view of equivalence, 100 ml 0.1 normal HCl is equivalent to 100 ml 0.1 normal ammonia, because 1 HCl is equivalent to 1 ammonia in this reaction. 1 NH3 plus 1 HCl is 1 NH4Cl. Do you follow? This is 1:1 reaction. So 100 milliliter of 0.1 normal HCl will be equivalent to 100 ml 0.1 normal ammonia. And what is the amount of ammonia in 100 ml 0.1 normal ammonia? The equivalent mass of ammonia is 17, or the molecular mass is 17. NH3, 14 plus 3, that is equal to 17. So how much ammonia will be present in this 100 ml 0.1 normal? It will be equal to 100 by 1000, okay, into 0.1 into 17. 100 ml 0.1 normal will contain 100 by 1000 into 0.1 equivalent, and that multiplied by the equivalent mass of ammonia 17, which is same as the molecular mass. The normality is same as molarity in this case of HCl and NH3, because one is a monoacidic base and the other is a monobasic acid. So it's a 1:1 reaction, and therefore the number of moles is 100 by 1000 into 0.1. So that multiplied by the molecular mass will give you the amount of nitrogen, the amount of ammonia, and instead of 17, suppose you put it 14, because 17 grams of ammonia will contain 14 grams of nitrogen. So it will be 100 by 1000, okay, 100 by 1000 into 0.1 into 14 will be the number of grams of nitrogen. So it is equal to 100 by 1000. You can simplify. You can get 0.1 into 1.4 divided by, that's equal to 0.1. 0.14 gram. And if it is 0.14 gram nitrogen present in 0.31 gram of the compound, the percentage will be given by 0.14 by 0.31 multiplied by 100. That will be the percentage of nitrogen of the compound. Okay. So percentage of nitrogen in the compound will be equal to the mass of nitrogen, that is 0.14, divided by the mass of compound, 0.31 into 100. So this will work out to be 45.16%. The value is 45.16%. Around 45, that will do, because the other values given are 90, 22, 11. So it is easy to choose from the answers. You need not do the exact calculation corrected to 3 decimal places. It's not needed. You can work out, say, with respect to 1 decimal place or not even decimal place. You take only the value other than the decimal values. You take the whole number values, you round to the nearest integer and get the value. It will be 45, and here the value given is 45.6. So it's a very simple problem. You are reminded of the Gel-Dahl method. The last part of the calculation, Gel-Dahl method, is also similar. 100 ml 0.1 normal HCl is the reacted acid. The reacted acid is equivalent to ammonia. That is how we study in Gel-Dahl's method. The reacted acid is equivalent to ammonia. So here the reacted acid is 100 ml 0.1 normal HCl, and that is equivalent to ammonia, and it is same as 100 ml 0.1 normal ammonia, and 100 ml 0.1 normal ammonia is same as 100 ml 0.1 molar ammonia, and 100 ml 0.1 molar ammonia will be equal to 100 by 1000 into 0.1 mole multiplied by molecular mass will be the number of grams of ammonia, and instead of 17, if you put 14, it will be number of grams of nitrogen, that is 0.14. So the percentage of nitrogen is 0.14 by 0.31 into 100. Do you follow? So that's the problem number 9. Question number 9, that again is a numerical calculation based on acid-base reaction between ammonia and nitrogen. Reminded of the Gel-Dahl's method. Gel-Dahl's method is very important. So they have, in many question papers, you find question relating to Gel-Dahl method. Need not be direct as such, but some part of it may be as you see in this particular problem. And then we have some questions from chemical bonding, which is correctly matched. That's a routine type of question. And if a students have raised, if you refer page 109 of the Mentor volume 1, which is given to all you students, you will see a very detailed list of molecules showing the hybridization of the molecules and also the geometry, the basic geometry, and then the actual geometry of the molecule. A large number of examples are given, and you please go through that and study all the examples very thoroughly, because you are always, there is a good chance, you have always a good chance to get questions relating to hybridization, VSEPR theory, structure of molecule, shape of molecule, the number of lone pairs. All these things are very often asked. So you have to be thorough with it. And all the examples given, I must say, are from that list. And we can just recall XCO3. If a student who is thorough about it, then immediately he will say XCO3 has a basic shape is tetrahedral because it is sp3 hybridization, and it works out to be a pyramidal shape because the xenon has lone pair. Apart from the electrons which have been used for bond formation, the XCO3, it is this molecule double bond O, double bond O. So the xenon has used 6 of the electrons and you have 1 lone pair on nitrogen. It is like, in principle, it is like ammonia molecule, XeO3. Only thing is that the XeO bonds are double bonds. So the hybridization is sp3. It is sp3 hybridization. So the basic shape is tetrahedral, but one corner of the tetrahedron is occupied by the lone pair. So actually, the actual shape of the molecule works out to be pyramidal. It is pyramidal shape, sp3 hybridization, and pyramidal shape XeO3. So the first one is not rightly matched. So A is the one which is not rightly matched. And we can also have a quick look at what will be the other cases. ClF3. ClF3 is a T-shaped molecule. The sp3 dehybridization, okay, sp3 dehybridization, T-shape. XeO4 molecule is a square pyramidal molecule. ClF3 is a T-shaped molecule. It is Cl, F, F, F. Out of the ClF3, you have chlorine having 7 electrons, only 3 electrons. That means the chlorine has 2 lone pairs. 2 lone pairs. So this is ClF3. Okay, ClF3 molecule. It is T-shaped molecule. It is T-shaped molecule. Okay, it is sp3 dehybridization. XeOF4 molecule is square pyramidal. It is sp3 D2 hybridization. Okay, with 1 lone pair. So it is square pyramidal. XeOF4, you have the 4 fluorine atoms. Fluorine, 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 fluorine. Then you have, okay, here you have the xenon atom, and here you have the double bond oxygen. So that's the molecule. It is sp3 D2 hybridization, and you have 4 electrons of xenon here and 2 electrons, 6, again a lone pair. So here you have a lone pair. So this is the shape, that is square pyramidal shape of XeOF4 molecule. And XeF2 molecule obviously is a linear molecule. The hybridization is again sp3d with Xe, F, F, and here you have 3 lone pairs. Okay, that is trigonal bipyramidal arrangement. That is the basic shape with the 3 lone pairs at the equatorial positions and the 2 fluorine atoms at the axial positions. So the molecule works out to be a linear molecule. This is a linear molecule. XeF2 is a linear molecule. XeF, F, it's a linear molecule. XeOF4 is a square pyramidal molecule, and ClF3 is a T-shaped molecule, and XeO3 is a pyramidal molecule with a 1 lone pair on xenon. Basic shape is tetrahedral, and the hybridization is sp3. So this is very often a question for most examinations. So you study that part of VSEPR theory, basic shape of molecule, actual shape of molecule, and also the hybridization of the central atom in the molecule. So these things are given in the form of a table, a very detailed table in the mentor, where you have plenty of molecules, and you go through it at least a couple of times and try to keep in your mind. Because once such a question is asked, you can save time. Once you remember that, you can immediately answer the question within seconds, so that the extra time available can well be utilized for answering other questions. But this sort of a question is always very important. Some question on this aspect will definitely be there in the question paper, either the VSEPR model, or you have the hybridization and the type of hybridization, the geometry of the molecule, the number of lone pairs on the central atom in the molecule, or total number of lone pairs in the entire molecules. Questions of that type will be asked. So for example, if you are asked about the number of lone pairs of electrons on xenon atom, the central atom in the molecule, it is 3 lone pairs. And suppose you are asked the total number of lone pairs in the molecule HCF2, it is 3 lone pairs on xenon, and on each fluorine you have 3 lone pairs. So means on 2 fluorine you have 2 into 3, 6 lone pairs plus these 3, that will be 9 lone pairs in the whole molecule. Sometimes question of that type may also be asked. They may ask question on the number of lone pairs on the central atom, then you count only the lone pairs on the central atom. Sometimes they ask question on the number of lone pairs in the entire molecule, and then you will have to count the lone pairs not only in the central atom but also in the connecting atoms and try to give the correct answer. So questions of this type are very common. So you spend some time on this, you are sure to question for any examination for that matter, whether it is JEE Main or even NEET exam, you will get a question of this type, no doubt about it. Now coming to the next question, that is question number 11. Don't go panic with this sort of a structure. It's not that complicated a structure. So some organic chemistry is included in the question, but the question is about hybridization. So obviously it's a question from chemical bonding and molecular structure. Remember that particular chapter, chemical bonding and molecular structure, is connected to structures of molecules we subsequently study in all chapters including organic chemistry. So that's why they have purposely put an organic chemistry example. So here is a molecule, and on careful examination you will see that the left ring is a pyridine. It's a pyridine molecule, the pyridine structure. And you know that the nitrogen in pyridine has a lone pair on it. Nitrogen has a lone pair. Okay. The nitrogen has a lone pair on it. But this lone pair is not involved in the aromatic ring formation, because you have already the 3 pi bonds, 6 pi electrons which are conjugated and forming the aromatic system there. Pyridine is aromatic, you know. So the pyridine ring is aromatic. The nitrogen has a lone pair, right? So it is like a nitrogen forming one bond here, and a lone pair here. Here it's a double bond. So you need consider only the sigma bond. Pi bond need not be counted. So what will be the hybridization of nitrogen? The hybridization of nitrogen will be the hybridization which will give 3 sigma orbitals. This sigma orbital, this is sigma orbital, and this is a lone pair orbital. So that means the nitrogen is in the sp2 hybridized state. You know that aromatic ring systems, benzene, pyridine, etc., all the atoms are in the sp2 hybridized state. The carbon atoms are in the sp2 hybridized. So is the case with the nitrogen atom. It is in the sp2 hybridized state. Then only you can have a planarity. The condition for aromaticity, of course, those things also come here in this particular question. Aromaticity is planarity. Okay, planarity, conjugate system. There must be 4n plus 2 pi electrons. All those things are to be satisfied for a system to become aromatic. This is aromatic. Of course, it is conjugated. There are 3 pi bonds which are conjugated. It is planar. And 4n plus 2 pi electrons, that's okay. 6 pi electrons you have, which means the lone pair on the nitrogen is there, not involved in the delocalized pi electron system. So it is there on the nitrogen, a lone pair in its orbital, and therefore we can easily decide the hybridization of the nitrogen to be sp2. It has to be planar, that means it is sp2. And what about the other ring system connected to that? On careful examination of the structure, you will see that it is the pyrrole. That is the pyrrole ring system. And the pyrrole ring system also has the nitrogen with a lone pair, but this lone pair on nitrogen is actually involved in the resonance, isn't it? involved in the delocalization. You have the pi bond here, you have the pi bond here, you have the lone pair here. So the lone pair is actually involved in the aromatic 6 pi electron cloud. So here the lone pair on the nitrogen is involved in the delocalization process. So if it is involved in the delocalization process, this lone pair is involved in the delocalization process, and the ring is aromatic and planar, then this nitrogen also must be sp2 hybridized. That means you count only this bond and the hydrogen. So this is, you have to consider, and if this is part of a planar ring, obviously the nitrogen has to be in the sp2 hybridized state. If there were something else with a lone pair on nitrogen, it would have been sp3 hybridized, as the case with ammonia. Ammonia, you know, is sp3 hybridized, NH, NH, NH with a lone pair. But here the nitrogen being part of the ring, and the lone pair is involved in the delocalization, and the ring itself is planar, then it means the nitrogen has these 3 sigma structures here. The lone pair is involved in resonance. It is not fully remaining in a orbital. It is involved in the delocalization process. It is involved in the ring formation, the aromatic ring formation of 6 pi electrons, 6 pi electron cloud, and therefore the nitrogen in this molecule is sp2 hybridized. So it is sp2 and sp3, sp2 and sp2, and not sp2, sp3, because normally we expect nitrogen to be sp3 because it has the lone pair. You will count these 3 bonds and the lone pair, and you will say sp3 hybridization, but that is not true, because this lone pair is involved in the resonance, involved in the delocalization, and it is not residing on the nitrogen atom. Therefore the nitrogen is in the, moreover you can also understand it in the other way. It is a part of a planar ring system, and if that is to be satisfied, the nitrogen has to be in the sp2 hybridized state. So this nitrogen is sp2, this nitrogen is also sp2 hybridized. So both the nitrogens are sp2 hybridized, and therefore the answer is C. So you are likely to make mistake sp2 sp3, but that's not correct. The correct answer is sp2 sp2. So a simple question on hybridization, but you have to thoroughly examine the molecule. Also have to have in your mind the aromaticity and the planarity of the rings. One is the pyridine ring system, and the other is a pyrrole ring system. In the pyridine ring system, the lone pair of the nitrogen is not involved in resonance, whereas in the pyrrole ring system, the lone pair of the nitrogen is involved in the aromatic 6 pi electron cloud formation. Right? So that's the question. Okay. So the next question is, calculate or find the de Broglie wavelength of the electron in the first Bohr orbit. The first Bohr orbit, de Broglie wavelength. So a problem where you combine the Bohr principle and the de Broglie principle. And combining these two ideas, if the circumference of the electron orbit is to be in phase, the circumference of the orbit 2 pi r must be equal to a whole number of the wavelength of the electron. So that is the combined result. If you combine the concept of circular orbits for electrons as in Bohr theory and the wave concept of electron in de Broglie theory, for the circumference of the electron wave described by the electron wave to be in phase, the circumference of the electron orbit must be a whole number multiple of the wavelength of the axis. So this 2 pi r is equal to n lambda. So where n is a whole number, okay, 2 pi r is equal to n lambda. You can calculate lambda is equal to 2 pi r by n. And if it is the first Bohr orbit, the value of n is equal to 1, you can put n equal to 1. And the radius of the first Bohr orbit, the radius of the nth orbit is given by this relation. You must know that it is 0.529 n square by z. That is in general the expression for the radius. The expression for the Bohr radius, the expression for the radius of a Bohr orbit, Rn is equal to 0.529 n square by z in angstrom unit. This is the value. Okay. So here n is equal to 1 and z, the atomic number is also equal to 1. So the value of R is equal to 0.529 angstrom. So you can put the value 2 into 3.14 into the radius is 0.529 angstrom, that is into 10 raised to minus 8 centimeter. And when you convert into meter, divided by n, the value is 1. So you will get the value 2 into 3.14 into 0.529 into 10 raised to minus 10 meter. So that will be the wavelength, the de Broglie wavelength. And if you compute, I think you will get the value as 3.3. 3.3 into 10 raised to minus 10. 3.3 into 10 raised to minus 10, the answer is A. 3.3 into 10 raised to minus 10, that will be the answer. You can very easily simplify this. 2 into 3 is 6.28 into 0.5. So nearly 3. You will get the value 3. You exclude the decimal places, you get the value as 3. So 3 into 10 raised to minus. So it's a pretty simple problem. Only thing is that you must know the two relations. One is the electron wave to be in phase. The circumference of the circle described by the Bohr orbit must be equal to an integral multiple of the wavelength of the electron. So that is 2 pi r is equal to n lambda. That is the first relation that you have in your mind. So that lambda equal to 2 pi r by n. And here it is given that it is the first Bohr orbit. For the first Bohr orbit, the R1, the first Bohr orbit, the radius of the orbit is 0.529 angstrom. Actually, in general, you can study this general relationship. The radius of the nth orbit Rn is given by 0.529 n square divided by z, where n is the principal quantum number of the orbit and z is the atomic number. And the atomic number for hydrogen is 1. Okay, the first Bohr orbit of hydrogen, that is implied in the problem, and n is equal to 1, first Bohr orbit. So R1, the Bohr radius of the first orbit, that is 0.529. So you can directly actually substitute the result and solve, directly solve and get the relations. You must know these two relations. You remember these two relations. Actually, in the atomic structure chapter, you have the Ritz combination principle regarding the wave number. Wave number is equal to 1 by lambda equal to RH into that 1 by n1 square minus 1 by n2 square. That equation you must have. And you must also have in your mind the energy of electron in a hydrogen atom minus 2 pi square m e to the power of 4 by n square h square, etc. That sort of. And you must also remember this expression for the radius, and also remember the de Broglie relation connecting the relation connecting the de Broglie concept and the circumference of described by the Bohr orbit, which is 2 pi r, which is a circle. It is a circular orbit that is usually considered in the Bohr theory. The orbit is supposed to be circular, so the radius is r, then the circumference is 2 pi r. That 2 pi r must be equal to an integral multiple of the wavelength, that is n lambda, from which you can find lambda as 2 pi r by n and substitute for the radius from this relation. You get the de Broglie wavelength. It's a pretty simple problem. Only thing is that you must know this. These are important. These questions are important. Perhaps these questions or some of the questions are already from previous question papers. So questions of this type will be asked. So in atomic structure topic, what are the important relations one has to keep in your mind? You just wrote down on a piece of paper one by one and try to read this many a time. on many days, so that you will be thorough about all the equations. So when a problem type question, this type of question is asked, you can immediately work out within seconds, and there is no need of making any mistake in this problem, because this problem is a pretty simple problem. Only thing is, you must know the two relationships. Okay, so we have to move a little faster, then only we'll be able to complete all the discussions. So coming to the next question, that is 13. You are given certain molecules, but all these molecules, of course, the question is based on chemical bonding. But however, all these molecules are molecules that you come across in connection with your discussion in the beryllium chemistry, boron chemistry, aluminum chemistry, and all that. That means in connection with the S block and P block in 11th standard, you come across these molecules. B2H6, I think you know the molecule B2H6. Okay, B2H6 is a diborane molecule. I hope this is something which is again very often asked a question. The special structure of the diborane molecule, you know, where you have hydrogen bridge bonds in addition to normal bonds, and the bridge bonds are 3 center 2 electron bonds. 3 center 2 electron bonds. These bonds are the 3 center. 3 center means it binds 3 atoms. The bond binds 3 atoms at the same time, utilizing only 2 electrons. That's why it is called 2 center 2 electron bonds. 2 such bonds are there in the diborane molecule, and the diborane molecule therefore is very special. As you know, it's a truly electron deficient molecule. It is short of electrons for forming the routine type of chemical bonds in its structure. So here you have only 2 electrons binding 3 atoms. That means it is an electron deficient molecule. And the question is about what is the type of overlapping with the bridge bond. That's the question. So once the boron is bound to 4 atoms like this, the hybridization, normally the hybridization in BH3 is sp2 hybridization, but when that BH3 binds with another BH3 to form a structure of this type, the boron is already linked to 4 hydrogen atoms. The hybridization of the boron changes from sp2 to sp3 hybridization. So it is sp3 hybridization for boron here, and for this boron also it is sp3 hybridization. And for hydrogen it is s orbital. So the bridge bond is formed by the overlap of sp3 orbital, s orbital, and sp3. So that's the first one that is given. So the first one, A is correct. A is correct. Now what about Al2Cl6? Al-Cl3 in a similar way. Al-Cl3 is an electron deficient molecule. It is short of 2 electrons, and it forms the dimer Al2Cl6, and it is AlCl, Cl, Cl. Then here you have Al, Cl, Cl, and this is Cl. Okay, this is Cl. And here a bond from chlorine to aluminum, utilizing the lone pair on chlorine. You have 3 lone pairs, and here also you have 3 lone pairs, and utilizing that bond towards aluminum. And once the aluminum is bonded to 4 atoms, remember the hybridization state of AlC, aluminum in AlCl3 it was sp2, but once it is Al bound to 4 chlorine atoms, it changes from sp2 to sp3. So here again the hybridization is sp3, and this is also sp3. And for chlorine, there are 2 bonds here, and you have 2 lone pairs. Altogether the number of lone pairs plus bond pairs is 4, and therefore chlorine is in the sp3 hybridized state. This also is in the sp3 hybridized state. So the bridge bond formed is sp3, sp3, sp3. It is sp3, sp3, sp3. So that is also correct. So the answer B is also correct. B is also correct. And coming to the next molecule, that is BeCl2 twice, BeCl2 twice. BeCl2, normally the BeCl2 molecule, as you know, is linear. The hybridization of beryllium is sp hybridization in beryllium. BeCl2 molecule is a linear molecule. But when the BeCl2 forms the dimer, actually it forms polymer also, but in the vapor state it forms dimers, and that is given here, BeCl2 twice. Actually it will be like this, BeCl2 twice, BeCl, okay, BeCl, Cl, Cl. This is the molecule BeCl2 twice, the dimer molecule. Actually it can form a polymeric molecule where you have BlCl2 connected like this, BClCl, then again BClCl, again, no, it's not here, there is no bond, it is Cl. So this type of polymeric structure is also possible for BeCl2, but here in the question it is given the dimeric molecule BeCl2, okay, this is the dimer of BeCl2, and we find that here the beryllium is forming 3 bonds. That means it is sp2 hybridized state. Here it is Sb, and here the beryllium is forming 3 bonds. It is sp2 hybridized, and this chlorine here, okay, the bridge chlorine here, sp2, it has to be 2 bonds and 2 lone pairs. It has to be sp3, and therefore the bridge bond is formed by the sort of overlapping sp2, sp3, sp2. It is sp2, sp3, sp2, but what is given is sp2, 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 which is wrong. And the question is to find out the wrong choice, the incorrect answer. So the third answer is incorrect. It is given as sp2, 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 but it must be sp2, sp3, sp2, sp2, sp3, sp2, and not sp2, sp2, sp2. And the fourth molecule, Al2CH3 6 times, is very similar to Al2Cl6, and the bridge bond formation is again sp3, sp3, sp3. In Al2CH3 thrice, it is also Al, okay, it is CH3, and here you have CH3, Al, CH3, CH3, CH3. This is the molecule, and here it is. This is sp3 hybridized, this is sp3 hybridized, and this also is sp3 hybridized. So it is sp3, sp3, sp3. That's also correct. It is very similar to Al2Cl6. So the only wrong answer is BeCl2 twice. It is given as sp2, 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 but the actual thing. So questions of this type are really important, and these appear in connection with the descriptive chemistry, inorganic chemistry description of the S block elements, where you come across beryllium, and the P block elements, the group 13 elements, where you come across boron and aluminium. And the text, the NCERT text, all these things are given in very detail. So it is very important you underline those points, and when you revise, try to catch these things in your mind. Try to keep these things in your mind so that you are able to answer very quickly. So the type of bridge bond formed. I hope it is clear. We can move to the next question. Question number 14. So read the question carefully. Given that lambda 0 and lambda are threshold wavelength, a wavelength of incident light respectively, then what will be the velocity of the ejected electron from the metal surface? Okay. It's a very simple problem, isn't it? You know, when a photon strikes an electron, a part of the energy of the photon is given to the electron for overcoming the attractive force, which is known as the threshold frequency, and the remaining amount of the energy is given out in the form of kinetic energy. So that the kinetic energy of the photoelectron half mv square is equal to the energy of the incident photon hc by lambda minus the threshold energy hc by, you can write hc by lambda. I put that threshold energy as hc by lambda 0. The wavelength corresponding to the threshold wavelength is lambda 0. So h nu minus h nu 0, which is same as hc by lambda. This can be written as h nu minus h nu 0. Okay. So that is hc by lambda minus hc by lambda 0, where lambda is the wavelength of the incident photon and lambda 0 is the wavelength corresponding to the threshold frequency, and the kinetic energy is the difference between these two, half mv square is equal to hc lambda. So that's a simple relation from which you work out this relationship. What will be the expression free? You have to find out. So v square is equal to, from this is equal to v square half mv square is equal to this much. So v square is equal to, what is v square? You can write it is 2hc by m, 2hc by m into 1 by lambda minus 1 by lambda 0. Okay. So that's equal to 2hc by m, okay, into lambda 0 minus lambda by lambda into lambda 0. So that v is equal to the square root of this value 2hc by m, okay, into lambda 0 minus lambda by lambda 0. That's the relationship. Very simple expression, just the Einstein's photoelectric equation. This equation is what you call the Einstein's photoelectric equation. Just rearrange the photoelectric equation and find out the expression for the velocity v of the ejected electron. Obviously the answer is C, square root of 2hc by m. That's a pretty simple question. It belongs to that 8 or 10 questions which I told you will be very simple questions in the question paper. So this particular question belongs to that category of very simple questions. It's a direct question, so direct that you can work out it from knowing that Einstein's photoelectric equation regarding photoelectric effect. Okay, I think it's very easily understood. Okay. And now you have a question again based on chemical bonding and structure, where you have a number of molecules and ions, and it's very important that you know I ask you to refer page 106 of Mentor volume 1, where you have a complete list of molecules and ions, simple molecules and ions, with a knowledge on the VSEPR model, the hybridization, the basic shape, the axial shape, and the bond angles. So refer that. Otherwise, for so many molecules, you will have to start from the first principles. You will have to write the electronic configuration, and then the promotion of electron to vacant orbitals, then hybridization and all that, and then work out the geometry and all that. To work out for all these molecules in a short time may be difficult. So you must have in your mind the type of hybridization and the geometry of these molecules. Then things are very easy, things are well in your hand. You can easily write down the correct answer for questions of this type. ClF3, I told you earlier in connection with an earlier question that ClF3 is a T-shaped molecule. If ClF3 is a T-shaped molecule, then BrF3 will also be a T-shaped molecule. And this I3 minus molecule, I3 minus is I bound to 2I with a negative charge. Iodine has 7 electrons and the 2 electrons are utilized. So 5 plus 1, 6 electron. It has 3 lone pairs and bond pairs. It will be a trigonal bipyramid arrangement, and the central atom iodine and the 2 other iodine atoms will be at the axial position, so that I3 minus will have a linear shape. Remember that I3 minus, ICl2 minus, XCF2, all these are linear molecule with sp3 dihybridite, and the basic shape is trigonal bipyramidal, with the atoms occupying the axial positions and the lone pairs occupying the equatorial positions. So they are linear. So One is T-shaped, this is T-shaped, whereas this is linear. That means all of them do not have the same structure. Of course, NO3 minus is planar triangular. NO3 minus is planar triangular. The central atom is sp2 hybridized, planar triangular. NO3 minus is planar triangular, sp2 hybridization. And SO4, you are four bond pairs and one lone pair. It is sp3 dehybridization, and it's a trigonal bipyramidal arrangement, and you locate the atoms, and the ultimate shape work has to be seesaw shape, SO4, seesaw shape. Then XCF4 is a square planar molecule. SO4 is seesaw shape. It's a seesaw shape. XCF4 is square planar molecule. XC. Okay. 4 electrons used, 2 lone pairs remain. They are the orbitals are at the axial positions, and therefore the shape of the molecule works out to be XCF4, also square planar. And SO4 and TeF4 will have nearly the same shape, because sulfur, selenium, tellurium, they belong to the same group in the periodic table. So that the TeF4 you can guess to have a shape similar to SO4. So that is seesaw shape. And NO3 minus is planar triangular. That means all the 4 molecules do not have the same structure. So B is not the answer. Now what about C? C, BF3 is, we already said it is a planar triangular molecule, BF3, planar triangular with the central atom sp2 hybridized. SO3 is again a planar, SO3 is this, planar, the central atom sp2 hybridized, planar molecule. And BRF3, we already said it is a T-shaped molecule. BRF3 is a T-shaped molecule. T-shaped molecule, okay? T-shaped molecule. It has 2 lone pairs, okay? And then CO3 2 minus. CO3 2 minus is C double bond O, O minus. This is the CO3 2 minus, where the carbon is sp2 hybridized, and therefore it's planar. So you don't find all of them to have the same structure. This is planar, this is planar, this is planar, but this is not. It is T-shaped. Now what about these 3? BF3 is planar, okay? SO3 is planar, I already said. And BH3 is also planar. We already said in the previous problem connection with the B2H6, and CO3 2 minus is planar. That means all these are planar molecules with the central atom in the sp2 hybridized state. All are planar molecules. That means the answer 4 is correct. A good question where you must know all details regarding all these molecules. So again, I tell you, open page 106 of Mentor 1 and look at the table containing all the molecules on which questions will be asked actually. It's a very exhaustive list of molecules and ions where very detailed regarding the VSEPR model and hybridization and geometry are given. I repeat, you go to those examples, study them thoroughly so that you are sure to answer questions relating to this without any mistake. Now again a question on atomic structure. The kinetic energy of an electron in the second Bohr orbit of a hydrogen atom is kinetic energy. Kinetic energy, as you know, is half mv square. Kinetic energy in the second Bohr orbit of a hydrogen atom. Okay, that's the question. Half mv square is the kinetic energy. But you have another important relationship that the mvr is equal to nh by 2 pi, that is the quantization of angular momentum in a Bohr orbit. mvr is equal to nh by 2 pi, from which you can get a relationship for r, mv square, half mv square, from which you can get a relationship for mass into, or mv square, you can get a relation from this mv square, from this mv is equal to nh by 2 pi r, okay, mv equal to nh by 2 pi r. So mv square will be, you will have to multiply this with v, mv square, mv equal to nh by 2 pi. So that m square v square you can square. This is equal to n square h square by 4 pi square r square, 4 pi square r square. So that mv square is equal to n square h square by 4 pi square r square, okay, divided by m, 1 m from this side brought to this side. So this is expression for mv square. So that kinetic energy equal to half mv square will be equal to half into this much. So that is n square h square divided by 2 into 4, 8 pi m pi square 8 pi square m r square. So that's the expression for kinetic energy. But in terms of Bohr radius, I have already told you the relationship for Bohr radius. The Bohr radius is given by Rn is equal to Rn equal to the radius of the first Bohr orbit, that is a0. The Bohr radius is given as a0 into n square by z, where z is equal to 1 for hydrogen, and n in the second Bohr orbit, n is equal to 2 here, n is equal to 2, z is equal to 1. So that r you can put it as r equal to a0 into 2 square, that is equal to 4a0, and plug that value here for r. You will get n square h square by 8 into 4, that is equal to 32. Okay, 32. Pi square is there, m is equal to there, and you get a0 square. So this is the relationship that you get, n square h square by n square h square divided by 32 pi square m a0 square, where a0 is the first Bohr radius. So it's a simple derivation. It's the combining the two relations. Kinetic energy is equal to half mv square and mvr is equal to nh by 2 pi. That is the condition for quantization of angular momentum applicable to electron in Bohr theory. And this expression also you must keep in mind. I told you this relationship before. Rn is equal to a0 into n square by z, where a0 is the first Bohr radius and n is the quantum number of that particular orbit or the electron in that orbit, and z is the atomic number, which for hydrogen is 1. So n is equal to 2, z is equal to 1, so it is equal to 4a0. So substitute 4a0 here for r, you get the expression for kinetic energy. Among the given equations, the correct equation given is therefore C. C is the correct equation, h square by you have h square by 32 m square m a0 square. So that's the equation that you get. Okay. Now question 17, that is again a pretty simple question based on the psi function, the things that you study towards the end of the chapter atomic structure. You study a little bit of quantum mechanics there, the Schrodinger equation, the solution of the Schrodinger equation and the acceptable solutions, give knowledge about the orbitals of the electron in that atom, and that is represented in terms of psi, and the probability relations, you know, the plot of psi against internuclear distance, not internuclear, the distance of the electron from the nucleus, that is psi against r, and you also have the plot of 4 pi r square psi square against r. Those plots you remember, but here the question is very simple. 4 statements are given. When you speak about the probability of an electron, the probability can be considered in 2 ways. One is the radial probability, which is given in terms of the quantum number n, and the angular probability, which is given in terms of the quantum numbers L and M. So the radial probability in terms of the radius r, the angular probability in terms of the other quantum numbers, and where you have these values which are the theta and phi, the two angles about which I do know we have not studied too much. We have just seen only the basics of that. The basics is this: the probability, two aspects. One is the radial probability given in terms of r, and the other is the angular probability given in terms of theta and phi. So there are 4 statements given. Check what all statements are correct from the given. Psi square, modulus of psi square. Now why modulus of psi square? Because psi may contain a complex number. If psi contains a complex number, then the psi square is positive, and the modulus of psi is obviously a positive value, and the probability of finding electron is always positive. That's why you take the modulus of psi square as the electron probability density at a point. That's a very correct statement. Psi and psi square modulus vary as a function of 3 coordinates. One is the radial coordinate, that is r, and the other is the coordinates representing the angular part of the wave function, that is theta and phi. That also is correct. It's a routine statement. And the third is one which I have already mentioned: the angular wave function theta phi depends only on L and ML, or L and M, and is independent of n, whereas the radial wave function is dependent on n. So statement C is also correct, which means all the 3 statements given A, B, C are correct. So that's a pretty simple question. Only the routine statements are asked, and if you know the routine statements, things will be in your reach. And the next question, okay, which of the following acid-Lewis base interactions are associated with expansion of octet? This again is a simple question, but only thing is that you have to be very careful while answering the question. SbF5. Look at that molecule, antimony. Antimony, nitrogen, phosphorus, arsenic, antimony, bismuth. It's a 5th group element, 15th group element containing 5 electrons in the outermost orbit. So all the 5 electrons have been utilized for forming bonds. That means there are 10 electrons in the valence shell. It's already a molecule which has crossed the octet. It's a molecule which violates the octet. Now it has 10 electrons already in SbF5 in the valence shell. But when it forms the complex SbF6, where that H is H plus and SbF6 is SbF6 minus, you find that the antimony is bound to 6 fluorine atoms. And for binding with the 6 fluorine atoms, you require 6 electrons. That means there are 6 electron pairs in the valence shell of antimony. 5 its own electrons plus negative charge 6 plus the 6 electrons from the 6 fluorine atoms will make a total of 12 electrons. That means there is an increase in the number of electrons from 10 to 12. That means there is an expansion of the octet. Already it was 2 electrons more than the octet. From antimony, you have antimony pentafluoride, which has 10 electrons in the valence shell, and now in forming this complex, it has 12 electrons in the valence shell. That means there is an expansion of the octet. This sort of phenomenon is what you call expansion of the octet during bond formation. So in the first case, there is expansion of octet. What about the second case? What about the second case? NH3BF3. NH3, okay, this is a classical example. NH3BF3 interaction. BF3 has only 6 electrons, but when NH3 and BF3 combine, a bond is formed between nitrogen and boron, utilizing the electron pair on the nitrogen. And now that nitrogen has 8 electrons in the valence shell, and boron also has 8 electrons in the valence shell. Boron, originally it was 6, but now it has acquired 8 electrons. In the combined molecule, both nitrogen and boron have 8 electrons in the outermost. That means both have the correct octet. There is no expansion from octet in bond formation in this case. So there is no expansion. Here there is expansion and here no expansion. Okay. In AlCl3 and Cl minus giving AlCl4. AlCl3, we already said earlier, it's an electron deficient molecule. It has only 6 electrons in AlCl3. AlCl3, you have only 6 electrons. But when it binds with the Cl minus, okay, to form AlCl4 minus ion, the aluminum is now bound with 4 chlorine atoms. So it has 4 into 2, 8 electrons. The 3 electrons plus the 4 electrons from the chlorine and the 1 electron free here. So now the aluminum has 8 electron structures and therefore there is no expansion. Expansion of octet. Octet means 8. If it is only more than 8, it is called octet expansion. So in this case, there is no expansion. But what about the last case? SO4. Sulfur has 6 electrons, of which 4 electrons have been utilized forming 4 bonds. So the sulfur has now 6 plus 4, 10 electrons on the sulfur atom in SF4, right? And when it combines with F minus forming SF5 minus, what is the number of electrons? Sulfur has 6 electrons. From 5 fluorine atoms, 5 electrons, plus the negative charge, that is 1 electron, you have 12 electrons. That means there is an expansion of the octet from 10 to 12. 10 to 12 in the last case also. 10 to 12. So in 2 cases, you have expansion. It's a more than one correct answer type question, of course. It is put here. But there are 2 answers here. A is an answer and D is also an answer. Both are correct. In both cases, you find it. It's a simple question. Only thing is that you have to count the number of electrons. It is more than 8 electrons. It is called expansion of octet. So check whether there is more than 8 electron formation during the process. In that case, it is octet expansion. Okay, octet expansion. Now let me rush a little bit so that I will be able to complete all the questions. And this is a very standard question, a very simple question. You might have answered questions of this type. The nodes are given, the radial nodes are given by n minus L minus 1. The angular nodes are given by L. And the total number of nodes are given by n minus 1 plus L, that is equal to n minus 1. So n minus 1 is the total number of nodes, and L is the number of angular nodes, okay, and n minus L minus 1 is the number of radial nodes. So these are the relations that you have to keep in your mind. I think all of you have these relations in your mind. Then solving the question is pretty easy. For 3s, for s, L equal to 0, n is equal to 3. So for 3s, it will be 3 minus 0 minus 1. So that is equal to 3 minus 1 is equal to 2. Okay. And for 2p electron, n is equal to 2 and L is equal to 1. Therefore, n minus L minus 1 will be 2 minus 1 minus 1. So that is equal to 0. So the answer is 2 and 0. For 3s, the number of radial nodes is 2, and for 2p, the number of radial nodes is 0. So very straightforward, very, very simple question. Only thing is that you must remember these relations. If you don't know, you keep these things in your mind. You study it right now, that the total number of radial nodes is n minus L minus 1. The total number of angular nodes is L, and the total number of nodes, both the radial and angular together, it is given by n minus 1. Okay. Now, coming to molecular orbital theory, you have common features among the species Cn minus, CON, NO plus and N2. Just by looking at these molecules, carbon has 6 electrons, nitrogen 7, 8 plus 7, 15, 8 plus 7, 6 plus 7, 13 plus 1. So here you have 14 electrons. For CO, 8 plus 6, 14 electrons. NO plus 8 plus 7, 15. One positive charge means 1 electron is lost. That means 14 electrons. For N2 also you have 14 electrons. That means all these have the same number of electrons, 14 electrons, which means they are all diatomic and they have the same electronic configuration. And what's the electronic configuration? Sigma 1s2, sigma 1s star 2, sigma 2s2, sigma 2s star 2, okay, pi 2py 2, pi 2pz2, 6, 8, 10, 12, and then, okay, sigma 2pz2. And therefore, the bond order you calculate, you know the bond order, you calculate from this electronic configuration. You have 4, 6, 8, 10. 10 minus number of electrons in antibonding is 4, so it is equal to 6 by 2, that is equal to 3. 3 is the bond order. That means all of them have the bond order 3, and all of them are having the same number of electrons, and the species having the same number of electrons are known as isoelectronic. So they are isoelectronic, and no unpaired electrons are there. That means the systems are diamagnetic. So all of them are isoelectronic, all of them are diamagnetic, and all of them have bond order 3. So it's a routine question. So what you have to do is just count the number of electrons, and if you find that the number of diatomic molecules, not complex structures, diatomic molecule is a direct application LCAO, that is a simple molecular orbiter theory to diatomic molecules. So you find the same number of electrons, count the number of electrons, you find the same number of electrons. In same number of electrons means same electronic configuration, and on the basis of the electronic configuration, you calculate the bond order and see whether unpaired electrons are there. If no unpaired electron, it is diamagnetic, and therefore isoelectronic, diamagnetic, and bond order 3. That answer B is correct. Okay, answer B is correct. Now coming to the numerical questions, I think we have some 13 minutes. I think that is sufficient, because all these numerical questions are pretty simple questions. 4 gram, this is a question from previous question, most probably I think from JE 2021 question paper, one question paper from JE 2021. I purposefully put that question in the question paper. It's a very simple question. 4 gram EQ molecular mixture of NaOH and Na2CO3 contain X gram NaOH and Y gram Na2CO3. What is the value of X in gram, nearest integer? That's the question. So how will you solve the problem? The total mass is 4 gram. So the 4 gram is equal to mass of NaOH plus mass of Na2CO3. And it is given that it's an equimolar mixture. Assume that they contains a mole. So a mole of NaOH and a mole Na2CO3. Both have the same number of moles. Okay? Equimolar, that means same number of moles. So naturally, the a mole of NaOH will have mass, number of moles, multiplied by molar mass, which is 40 for NaOH. NaOH molar mass is 40. 23 plus 16 plus 1 is equal to 40. So it will be A into 40. That will be the mass of NaOH. And sodium carbonate, what will be the molar mass? It is 46 plus carbon 12 plus 48, making a total of 106, I think. Okay, so what will be the number of grams of Na2CO3? It will be equal to the number of moles, which is A, the same, multiplied by 106. So this is equal to 4. You can easily solve and get the value of A. It is 106 plus 1, that is 146 A. So A is equal to 4 by 146. Pretty simple. So that is A. And what is A? Number of moles of NaOH. So what will be the grams of NaOH? 4 by 40, again 146 into 40. So many gram of NaOH. X gram of NaOH is given. So this is the value of X. The problem is very easily solved, and you can get the nearest integer. You will get a value approximately 4 by, it is 4 by 146 into 40. That is equal to 160 by 146. You will get a value 1 point something. But you are asked to correct it to the nearest integer. That means you will get the answer 1. The answer is 1. Pretty simple. Solved within few seconds. Problem. Pretty simple problem. So that belongs to the class of questions which I told you. There will always be some 8 to 10 questions which are very simple questions. So this is an example of such a question. Very simple question. And now here comes a question where you will have to think a little bit. The wavelength of the electron accelerated from rest through a potential difference of 40 kilovolt. That means 1000 volt. 40 into 1000 volt. That is 40 into 1000 volt it is. Okay, that is equal to 40,000 volt. Okay, that's the accelerating potential. And then the question is, what is the value of x? The wavelength of the electron accelerated from rest through a potential difference of 40 kilovolt is x into 10 raised to minus 12 meter. And what is the value of x? To the nearest integer is a question. You are given a lot of parameters. Mass of the electron is given, charge of the electron is given, and the Planck's constant is also given. And if the electron is accelerated, if the electron charge is accelerated through a potential V volt, the energy of the electron is given, the energy is given in terms of Q into V. The kinetic energy of the electron is given Q into V. So Q is given here as the value of the charge of electron. It is 1.6 into 10 raised to minus 19 coulomb, okay, multiplied by the accelerating potential, that is 40 into 1000, that is 40 into 1000 volt. So this will give you the kinetic energy in coulomb volt, and coulomb volt is nothing but joule. Coulomb volt is equal to joule. So the kinetic energy in joule will be given by 1.6 into 10 raised to minus 19 into 40 into 1000. And what will be the expression for the, what is the expression for the wavelength? What is the expression for the wavelength? What is the expression for the wavelength? Using the de Broglie's equation, lambda is equal to h by mv, and the kinetic energy, that is equal to half mv square. Okay, so again you can write mv square is equal to this half mv square. So mv square is equal to 2 into kinetic energy. Okay, so from this m square v square is equal to 2m kinetic energy. Okay, so that mv is equal to square root of 2m kinetic energy. So that is from first principles. And normally students study this equation by heart. You proposed this equation here. So that lambda is equal to h by m into square root of 2m kinetic energy. So if you take that m into the square root, actually m is equal to 2m kinetic energy. So that yeah, this is okay. So if you substitute, what you get is 2m into q into v. So you can substitute for that. H lambda is equal to h by 2m kinetic energy. Did we make any mistake here? mv square is equal to 2 into kinetic energy. So m square v square is equal to 2m kinetic energy. So that mv is equal to square root of 2m kinetic energy. Okay, so lambda equal to h by mv, that is equal to h by square root of 2m kinetic energy. Only this much. This is not, there is no m here. This h by, I hope it is clear, h by square root of 2m kinetic energy. So you can substitute for h, 6.6 into 10 raised to minus 34 in SI unit, and then mass, that is again given in SI unit, 9.1 into 10 raised to minus 31 kilogram. Okay, and kinetic energy you have already calculated, 1.6 into 10 raised to minus 19 into 4000. Of course, there is a little bit of calculation here, and therefore lambda is equal to, I will write here, lambda is equal to 6.6 into 10 raised to minus 34. I write only one decimal place, square root of 2m. Okay, 2 into m is 9.1 into 10 raised to minus 31. Okay, into kinetic energy is 1.6 into 10 raised to minus 19 into, it is 40,000, that is 4 into 10 raised to 4. Okay, so here you can bring all these 10 to the powers together and take the square root and cancel with the 10 raised to minus 13, and here is square root of 2 into 9.1, 1.6, 4, and you take this as 9, then square root of 9 is 3, and here convert this into 16 by multiplying with the 10 and making this 10 raised to minus 20, so that 16 square root is 4 and square root of 4 is 2. So you have 9, that's square root 3, square root of 16 4, and square root of 4 2, and only thing is that you have to multiply them and multiply by square root of 2, which is 1.414, and bring all the 10 to the powers together and bring to the numerator, and then solve this resulting equation. I leave it to you. You can solve this equation, you can solve this relation and get the value of lambda, and you will see that the value of lambda in this case corrected to the actually the value is x into that lambda is given as x into 10 raised to minus 12. So when you correct to the nearest integer, I think you will get a value 6. It will be 6 point something, but corrected to the nearest integer. It is 6 because it is single integer type of questions. So that's why they always give in the bracket nearest to the integer, nearest integer. Okay. So you can easily, only thing is that a little bit of calculations, there some numerical ability is also tested in this equation, whether you are able to calculate within the stipulated time and come to the correct result. Okay. So the problem is solved because lambda equal to h by mv is one relation that you have to keep in mind. And the other relation that you have to keep in mind is mv is equal to square root of 2m kinetic energies. mv is equal to square root of 2m kinetic energies, so that lambda equal to h by square root of 2m kinetic energy. This is equation which is usually studied by students by heart, h by square root of 2m kinetic energy. So that's the de Broglie wavelength you can calculate directly by knowing the kinetic energy. Then the other parameters, Planck's constant and mass of electron. Okay, that's the problem. A good problem, but not at all difficult. Not at all difficult. Now the next question is again the simplest of all the questions, I think. The simplest of all the questions. Okay, we will have only 3 more questions, 23, 24 and 25, and I think I will take hardly 3 minutes for that. The azimuthal quantum number for the valence electron is Ga plus. Actually it is aluminium 13, and the next element in the periodic table is gallium in the next period. So the next period means there will be an increase in atomic number by 18 units, so that the gallium will have an atomic number 31. So you are not given the atomic number of gallium, but instead you are given the atomic number of aluminium. It is 13 plus 18 will be the atomic number of gallium 31. So naturally the configuration will be 1s2, 2s2, 2p6, okay, 3s2, 3p6, then 3d10, then 4s2, 4p1 for gallium. And if that one electron is lost from gallium ion, the one electron is lost. Therefore, the outermost electron as far as gallium ion is concerned is in an s orbital. And therefore, the azimuthal quantum number for that orbital is L equal to 0. So the answer is 0, L equal to 0. The azimuthal quantum number for the 4s orbital is 0. So a pretty simple question, but that question was asked in the JEE question paper last year. Okay, so I have purposefully put such questions just to make you aware that even simple questions like this are asked. There will be at least some simple questions, but don't make mistakes with these simple questions. Remember, for aluminum it is 13, and therefore gallium it is 31. So the electronic configuration gallium, that one electron is lost, that means the outermost electron is 4s, and therefore the valence electron has azimuthal quantum number L equal to 0. Okay, that's fine. And this is 250 ml of 0.5 molar NaOH was added to 500 ml of 1 molar HCl. It is 250 ml 0.5 molar NaOH, okay, mixed with 500 ml 1 molar HCl. Without using any arithmetic equations to solve this problem, suppose you first think from first principles. It is better in such problems is think from first principles. 500 ml 1 molar HCl will be equivalent to 1000 ml 0.5 molar HCl. Molarity is 1. If you make the molarity 0.5, you have to increase the volume, you have to double the volume. So it is 1000 ml 0.5 molar HCl. So what about the neutralization? It is a 1:1 equation for NaOH and HCl, 1 NaOH, 1 HCl. Okay, so 250 ml 0.5 molar NaOH will be exactly neutralized by 250 ml 0.5 molar HCl. That means out of the 1000 ml 0.5 molar HCl, what remains is 750 ml 0.5 molar HCl. Okay, 750 ml 0.5 molar HCl. And 750 ml 0.5 molar HCl is equal to what? How much? Is equal to 750 by 1000 into 0.5 mole. Okay, so what will be the number of molecules? This multiplied by, this is 3, this is 4. Okay, so it is 1.5 by 4, 1.5 by 4 multiplied by 6 into 10 raised to 23. 1 mole is 6.02 into 10 raised to 23. So obviously by finding the number of moles and multiplying by Avogadro number, you will get the number of molecules. That's a simple question. Only thing is that you must be able to do this sort of a thing in your mind using the first principles, that 500 ml 1 molar HCl is equal to 1000 ml 0.5 molar HCl, right? When the concentration is half, the volume is doubled, that's all. And 250 ml 0.5 molar NaOH will be exactly neutralized with the 250 ml 0.5 molar HCl. So what remains is 750 ml 0.5 molar HCl, and calculate the number of moles in 750 ml 0.5 molar HCl. It is 750 by 1000 into 0.5. That is equal to 1.5 by 4 into 6 into 10 raised to 23, and you get the answer. I think you will get the answer as 6. You will get this relation 1.5 into 6 divided by 4. But his answer, the answer will be, it is 9 by 4, isn't it? (1.5 by 4 into 6). 1.5 by 4 into 6. So it is 6, 9 by 4. So that's equal to, okay, 2.25. So that into 10 raised to 23. The question is into 10 raised to 21. So when you make it 10 raised to 21, you will get it as 225 into 10 raised to 21. So x into 10 raised to 21 was the question. So that x is 225. You get it as 225. That's a simple question, I think. All of you have followed the question again from first principles. You understand, be thorough with the first principles. That will help you rather than recollecting all the ready-made expressions. Better in such questions to think from the first principles. But you must be able to do it quickly so that you must take minimum time for answering the question. Okay. And now we have the last question in this question paper. How many of the following has a bond order 3? It's a repeat. I don't know how that question was repeated. Actually, it is a question very similar to question number 2. And all these ions and molecules given are diatomic molecules. And the question is, which of the following molecules has a bond order 3? Questions of this type are very common in today's question paper. Particularly in the JEE advanced question paper, you find questions of this type. How many? And if it is 7, if you write 6, the mark is gone. So you must be able to pick the correct number of molecules which have bond order 3. We have already said that the nitrogen molecule, N2 molecule, and we have already said the NO plus molecule. We have said the CO molecule. They have 14 electrons, and this also 8 plus 7, 15, minus 1, 14 electrons. This has 14 electrons, and count all others. O2 2 plus. O2 2 plus means 2 into 8, 16 minus 2. So O2 2 plus also has 14 electrons. O2 2 minus has 18 electrons. Then NO plus has 8 plus 7, 15, minus 1, 14 electrons. F2, 2 minus, that is 18, again 2, that means F2, 2 minus will have 20 electrons. And CO plus, 8 plus 6, 14, 1 electron is lost, that means it has 13 electrons. Then N2 minus, 14 plus 1, 15 electrons. And Cn minus, it is 8, 7 plus 6, 13 plus 1, 14 electrons. So 14 electrons. So how many of them? 14 electrons. You have N2 14 electrons. You have CO 14 electrons. You have NO plus 14 electrons. Okay, that is written 2 times. NO plus is written 2 times. So N2 14 electrons, CO 14 electrons. Okay, then O2 2 plus 14 electrons. And the last one, what is the last one? Cn minus 14 electrons. So N2, NO plus, CO, O2 2 plus, and Cn minus. All of them have 14 electrons. And 14 electrons means they have the configuration we have already said. Sigma 1s2, sigma 1s star 2, sigma 2s2, sigma 2s star 2, okay, pi 2py2, pi 2pz2, sigma 2pz2. We are making a bond order 10 minus 6 by 2, that's equal to 3. Bond order 3, all these molecules have bond order 3. The others, obviously bond order different from 3 because they have a different number of electrons. They are not isoelectronic. Isoelectronic means isoelectronic diatomic species will have the same bond order. So it is easy that you count the number of electrons 14 and you have bond order 3, and you find that these 5 have bond order 3. The bond order of others are not equal to 3. So that is again a question which is almost same as question number 20, and this is the type of question that is very often asked from the molecular orbital theory, where you study only diatomic molecules and some ions like O22 plus, O22 minus, F22 minus, CO plus, N2 minus, Cn minus, etc. So you can calculate the bond order, and there are surely questions of this type asked both in the JEE main paper and the advanced paper, and also for NEET you find some question which is asked on bond order or electronic configuration of diatomic molecules by applying molecular orbital theory, which is pretty easy for you to answer. All of you will be able to answer this question within seconds. So when a larger number of ions or molecules are given, you actually count from them molecules having the same number of electrons. If you have the same number of electrons, they are isoelectronic. Remember, all of them will have the same bond order. So to start with, you count N2, it is N triple bond N, bond order is 3, even otherwise we know bond order 3 for nitrogen. Then build up the electron configurations of other molecules and find the bond order. So dear students, I think you have understood the discussion, and now the time is over. It is 8:10. We have to finish at 8 p.m. And I think I have explained the things in whatever detail, and you will be able to understand what has been discussed. And keep in mind that questions of this type are often asked for examination, and that's important. Of course, it's 3 big chapters. We have covered only 25 questions, so a lot of things remain there, but these questions are representative sort of questions, very often asked, repeatedly asked in question papers. So focus on them, and wish you all the best. Good night. Okay.